This is Chem 230, Introductory Organic Chemistry at Glendale Community College in Glendale, Arizona, and today we're going to talk a little bit about some of the predictions you could make for atoms based on the number of electrons they have and the Lewis structure for those atoms. So one of the things that a lot of people do is they think about what atoms are trying to do as if atoms have wills and goals and those types of things. So in that phrasing, atoms are trying to get a pseudo noble gas electron configuration. So what that means is that the noble gases are stable with the number of electrons they have and the electron configurations they have, and if some other species could be similar to the noble gas and electron configurations, it too would be stable. So by looking at the number of valence electrons in an atom, we can try to predict what the element is likely to do. Metals tend to lose electrons. Nonmetals tend to gain or share electrons in some sense because they want to get the same number of electrons in their environment that a noble gas has in its environment. So one of the first things we can do to look at that is to look at Lewis structures for sodium atoms and chlorine atoms, right? So sodium, and what Lewis structures do is they tell you where the valence electrons are. So Lewis structures, we're going to focus on the valence electrons, or the outer electrons, as they're often called as well, outer electrons. So if we look at sodium, 1s2, 2s2, 2p6, 3s1, right? The first and second energy levels are the inner energy levels, or we would refer to this as the core. And then the electrons in the outer energy level are the valence electrons. So in the sodium electron configuration, 10 of the electrons are the neon core, you would call it, the inner unreactive electrons. Then you have this one outer valence electron, which we would represent as simply a dot next to the sodium symbol. So sodium with the dot is the Lewis structure for the sodium atom. And as you could see, it's really, really close to the noble gas configuration of neon. Sodium, if you didn't look at the periodic table while I was working on this, you can see has 11 electrons. Neon has 10 electrons. So sodium is really, really close to neon. It just has to lose the one valence electron to have the same number of electrons as a neon. So if the sodium went ahead and lost that one valence electron, it would be a sodium plus ion, and then it would have the same number of electrons in the same electron configuration as neon, 1s2, 2s2, 2p6 for 10 electrons. And that's why metals, having just a few more electrons than noble gases, tend to lose those electrons and become cations. And this is something that Lewis would predict by writing the element symbol and putting the valence electrons as dots, and then you could watch as you lose those dots, have no valence electrons in the sodium plus, and it's stable like a noble gas. And that's the way sodium exists in nature, as a cation, not as a neutral element. Then chlorine, if we looked at chlorine, chlorine is 1s2, 2s2, 2p6. Again, how many electrons does a chlorine have? If you're familiar with this, you know 17 electrons for chlorine. You could look that up in the periodic table. And if you go ahead and fill up the orbitals in the right order, You get 1s2, 2s2, 2p6, 3s2, 3p5, which is 7 valence electrons. So you put 7 dots around the chlorine atom to represent the 7 valence electrons, and there's the Lewis structure for the chlorine atom. Now, if you're familiar again with the noble gases, argon is 1s2, 2s2, 2p6, 3s2, 3p6, which is just one more electron than chlorine, so 18 electrons. Again, 18 electrons, argon, there's the electron configuration. So all chlorine would have to do to have the same number of electrons as a noble gas is to gain one electron. So this chlorine has 7 valence electrons, right? Like sodium had 1 valence electron. The core electrons here, again the neon core, this has 7 valence electrons, and chlorine could theoretically lose 7 electrons to get to be the same number of electrons and same electron configuration as neon, but each time you lose an electron you get positively charged. When you're positively charged, you're not likely to give up any more electrons because a positive charge helps to hold those negative electrons in. So it's much easier for chlorine to gain 1 electron. And this S2P6 configuration, right, so once chlorine forms chloride with a negative charge and 8 valence electrons, it's going to be more stable. So again, in nature, you don't have chlorine atoms running around because the 7 valence electrons is an unstable number. You have 8 valence electrons in the chloride. So there we go, chloride was 1 electron away from a noble gas configuration, so it picks up that 1 electron to get 18 electrons, 1s2, 2s2, 2p6, 3s2, 3p6, the same as argon, and stable. So you basically can look and see, again for the S2p6, that's the origin of the octet rule, that having 8 valence electrons is stable, because then you filled the S and P sublevels, and once the sublevels are full, that's fairly stable. So the 8 valence electrons in the chloride is more stable than the 7 valence electrons in the chlorine. And so you can see how sodium, to get to a pseudo-noble gas configuration, would lose 1 electron. So I have the same electron configuration as a noble gas, the neon. Chlorine would just gain 1 electron to form chloride, and the nature of the ionic bond is not shared electrons like a covalent bond, but simply that if you have a positively charged ion like sodium, that would be attracted to anything negative like a chloride, so the sodium ion would be attracted to the chloride ion because they're opposite charges. That's the nature of the ionic bond. So if you look at any atom and count up the number of valence electrons, you can figure out how many bonds it would be likely to form by comparing it to noble gas and seeing if either gaining a few electrons or losing a few electrons would get it to the same number of electrons as a noble gas. That's what it's more likely to do.